Welcome to Tomorrow Unveiled, the show that extracts the crucial knowledge nuggets from the week's most important reports, giving you a comprehensive shortcut to being well-informed.
This past week was really a story of contrasts, wasn't it?
A complete paradox. On one hand, you have these incredible scientific breakthroughs, things happening in deep space that just expand what's possible.
Exactly, pushing the absolute boundaries of habitability of engineering. And then you turn around and look back at Earth.
And you're hit with these really critical, immediate challenges. We're talking massive cybersecurity failures, frustrating regulatory bottlenecks, and even just the fundamental health risks of being human in space.
It's the perfect summary.
Absolutely. It feels like that tension, that push and pull, it just defines the modern space sector right now. You have this unbounded ambition meeting these very real, very grounded terrestrial constraints.
Well said.
So our mission today is to take a whole stack of diverse reports compiled by our dedicated research team and really unpack the insights that have been corroborated across them. We're going to cover everything from Martian history to orbital infrastructure.
And of course, those persistent security and regulatory headaches that, frankly, threaten to slow down everything we're trying to build.
Right. And to make sense of it all, we've structured our analysis for you into three major areas.
First up, we have what we're calling a red planet shockwave. There's a discovery that just fundamentally changes the known timeline of liquid water and potential life on Mars.
Oh, okay.
Second, we're examining the Orbital Toolkit. This is all about how radical new materials and automated manufacturing techniques are trying to build a sustainable, actual economy beyond Earth.
And finally,
we tackle the earthly friction. All those critical vulnerabilities, from human isolation on the International Space Station to that massive security breach and that looming FAA deadline, all the things that are really testing our limits right here at home.
Okay, let's just dive straight in, starting with Mars. Because the news here is it's genuinely groundbreaking. It fundamentally changes the entire historical context of the red planet.
It really does.
For decades, the prevailing belief, the textbook answer in planetary science, was that Mars went through some catastrophic climate shift and just dried up roughly 3 billion years ago.
That was the timeline, and our entire search for life was defined by that date.
But now, according to the data our research team collected this week, that timeline has been, well, it's been fundamentally expanded.
And not by a little. We are talking about hundreds of millions of years.
So this isn't some minor adjustment.
Oh, no. This is a seismic shift in how we understand Martian climatic evolution. We are essentially rewriting the final chapter of Mars's wet period. The key discovery, the one that's corroborated across the data, comes from China's Zhurong rover,
which was exploring the southern Utopia Planitia, that huge plain.
That's the one. And the data it collected provides really convincing evidence of significant aqueous activity water remaining on the Martian surface until approximately 750 million years ago.
750 million years ago. I need to stop you there just to put that into perspective for everyone listening.
Please.
That pushes the wet history of Mars forward by several hundred million years. It takes it well into what's called the Middle to Late Amazonian period.
A period we all assumed was almost entirely a frozen, dry epoch.
Exactly. A wasteland. And suddenly, that entire span of time is back on the table for potential biological activity. I mean, this changes everything about where we might look for evidence of past or maybe even present life.
And what's so fascinating about this is how they found it. The subtlety of the finding is key.
Right. They weren't looking at obvious surface features, were they? Not like the giant canyons or the ancient riverbeds you can see in photos.
No, those features dried up billions of years ago, just like we thought. Instead, they were looking below the surface using incredibly sophisticated instrumentation.
What kind of tech are we talking about?
Specifically, high-frequency, quad-polarized ground-penetrating radar. You can think of it like this. It's basically performing a detailed CT scan of the Martian subsurface. It's probing what the surface has been hiding for eons.
A deep scan that goes beyond just what you see on the surface and reveals the history that's written in the planet's hidden layers. So how deep are we talking here?
It scanned down about 4 meters.
Okay. And what did the radar actually find that was the smoking gun for sustained water?
Well, what it detected wasn't just, some sporadic ice pockets or maybe volcanic debris. It found a remarkably uniform sedimentary layer, about 4 meters thick, just buried beneath the loose topsoil, the regolith.
And uniform is the key word there.
Uniform and continuous across the entire area the rover scanned. The researchers who analyzed this data were meticulous. They rigorously ruled out all the alternative dry explanations for how this layer could have formed.
Like what? What else could have made it?
Things like volcanic ash deposits from an eruption, or maybe wind-driven dune formation over millions of years. But neither of those processes would create a layer this uniform.
So the consistency of that layer, it's not just that they found something, but that it had to be stable, persistent water that laid down this sediment over a very long time, right?
Precisely. The uniformity and the continuity of that 4-meter thick layer beneath the surface is the definitive signature of a large, persistent body of water.
Wow.
The conclusion reached by the researchers is that this structure could only have been formed in a sustained aqueous environment, something like a shallow sea or maybe a very large lake that slowly deposited sediment over millions and millions of years.
And that process just kept going long after we thought Mars was bone dry.
Far longer than the scientific consensus previously allowed.
That's immense. I mean, if liquid water was there for that much longer, the window for potential biological activity, where something could have lived and left behind detectable biomarkers, is just vastly expanded.
It really is.
Before this finding, we were looking for ancient fossils from 3 billion years ago. Now, we're hunting for signs from a comparatively recent past. The question, are we alone, suddenly feels a lot more urgent.
And it has immediate strategic implications for future missions. It's not just an academic finding.
How so?
Landing sites that were previously dismissed, just written off as hopelessly dry because of their Amazonian-era geology, well, they all have to be rapidly reevaluated now.
Because they might be the prime spots.
They might be. And this discovery feeds directly into the current state of planetary science, where we're seeing this strange mix of tremendous progress from data analysis and at the same time, significant setbacks because of global politics and funding.
That's a critical connection to make. Our research team noted the recent and pretty politically driven cancellation of the joint European Space Agency and NASA Mars Sample Return Mission, the MSR.
A huge mission.
And that was attributed to heavy budgetary sanctions imposed by one of the partner nations. That was supposed to be the flagship effort, the one that would finally bring Martian rocks back to Earth for us to study.
Yes, the cancellation of MSR due to those budget constraints was a major blow to the scientific community. It forced the ESA to pivot its available resources somewhere else.
But there's a silver lining here, right?
Fortunately, yes. They have the ExoMars Rosalind Franklin rover, which is now scheduled for launch in 2028. And critically, that rover is purpose-built to dig deep. It has a drill specifically designed to penetrate 2 meters into the Martian soil.
2 meters. That is exactly what we need to hear right now. Given that the Xuron radar found this 4-meter-thick aqueous layer just under the surface, the Rosalind Franklin rover could potentially reach the upper parts of this newly identified wet history.
It's the perfect planetary science pivot. The data from one rover now directly informs the mission profile of another. It could potentially direct the ExoMars rover straight to the best possible places to look for biomarkers.
To sites that we now know were active long enough ago to potentially harbor signs of life, preserved just beneath the surface.
It turns a budgetary setback into a scientifically focused reprioritization. It's really quite remarkable.
So if that expansion of our scientific knowledge is the ambition, then the growth of the manufacturing and the supply chain here on Earth is the engine that actually drives the capability.
Good way to put it.
So let's transition from the red planet back to the infrastructure being built in our own orbit. The reports from this week really highlighted a major reliance on advanced manufacturing, specifically additive manufacturing, or AM, to achieve resilience.
Additive manufacturing, what most people just call 3D printing, is fundamentally driving aerospace resilience. It allows us to create stronger, lighter components much, much more quickly.
And our dedicated research team focused on this area and found some pretty significant growth projections.
Very significant. For one of the leading additive manufacturing providers, the Aerospace and Defense, or A&D business segment, is projected to grow over 20% in 2026.
20%. So this isn't just a niche market anymore.
Not at all. This segment is actually on track to become that company's largest industrial business overall.
And that kind of growth is robust, especially when you realize this is about production at scale. The reports mention revenue from production printing systems and custom metal parts is expected to exceed $35 million in 2026 for that one provider.
Right.
So that tells me we are far, far past the era of just using 3D printing for simple prototypes. We're using it for mission-critical, high-stress parts.
It absolutely is production. This growth isn't about novelty. It's fueled by the demand for incredibly high reliability components, particularly in demanding environments like, say, rocket propulsion systems and high-end satellite systems.
What's the key advantage? Why 3D print a rocket part instead of milling it from a block of metal?
The ability to create lightweight, consolidated designs that integrate these really complex features. Things like internal cooling channels or thermal management systems that are just impossible to achieve using traditional subtractive manufacturing.
So you can make one single part that does the job of 10 older parts.
Exactly. You reduce the part count, which increases reliability, and you save a ton of weight all at the same time. It's a win-win-win.
And we also see domestic security playing a huge policy-driven role here, which ties right back to supply chain stability.
A very big role.
Our research highlighted the strategic decision by manufacturers to expand their facilities, specifically adding up to 80,000 square feet in Littleton, Colorado, to create a specialized A&D application center of excellence.
And that strategic investment is designed explicitly to strengthen domestic supply chain resilience. This isn't just a business decision, it's a national security one.
And it's being pushed by government policy.
Heavily. It's supported by favorable U.S. policy tailwinds, particularly provisions that are embedded within the National Defense Authorization Act, the NDAA.
What do those provisions do?
They essentially restrict the Department of Defense from using foreign-sourced 3D printing systems for its critical programs. The U.S. is clearly prioritizing an end-to-end, entirely onshore metal additive manufacturing ecosystem.
So everything from the raw metal powder to the huge, large frame printers themselves
Has to be domestically controlled.
it makes sense.
Yeah.
You don't want a critical rocket engine component relying on a supply chain that could be politically or geographically cut off tomorrow.
Absolutely not.
And speaking of securing the supply chain, our sources reveal an even more radical approach than just domestic 3D printing. It seems they're looking to secure the very molecules of space travel.
That is a perfect way to describe it.
This leads perfectly into the next major breakthrough you highlighted.
Hmm.
Carbon fiber that doesn't rely on oil. We're talking about carbon-negative carbon fiber.
This is truly game-changing material science. Our research corroborated the validation of a really complex process to manufacture a high-quality carbon fiber precursor. It's called polyacrylonitrile, or PAN, using captured carbon dioxide as the primary feedstock.
Wait, let me get this straight. They are taking CO2, a major climate problem, and using energy to convert it into the base chemical for carbon fiber, one of the highest performing, most demanding industrial materials on Earth.
That's exactly right. The product, which they've named Huygens-C, utilizes a pathway that is both carbon negative because it's consuming CO2 and, critically, it's hydrogen cyanide free.
Which is a big deal, right? Is
Yeah.
that a major toxic byproduct in the traditional process?
It's a historical problem in traditional pan manufacturing, yes. This eliminates it. But the core takeaway here is that the CO2-derived material is chemically and structurally identical to the traditional versions that rely so heavily on petrochemicals derived from oil and coal.
So if it's chemically identical, that means it acts as a drop-in solution.
Precisely.
Manufacturers don't have to redesign their entire production line or requalify all their materials from scratch. They can just use this sustainable, secure domestic product tomorrow, and it meets all the rigorous performance standards for everything from aircraft structures to satellite components.
It secures the supply line, it removes a reliance on volatile global oil markets, and it dramatically reduces the industry's environmental footprint all at the same time. It's a massive step forward.
And speaking of high performance, the ability to manage heat in these next-generation components is absolutely essential, especially as systems get smaller, faster, and more powerful.
Which brings us right down to the nanoscale solutions.
Right. Thermal management is a major technical hurdle for everything from high-power electric aviation batteries to the bodies of hypersonic vehicles. You can't just slap a bigger, heavier radiator on a satellite. Weight is everything.
You certainly cannot. This is where nanomaterials entered the discussion. We're seeing some really innovative materials being developed, specifically materials like Al2O3 aerogels, that's aluminum oxide, which are then reinforced with graphene nanorods.
Okay, so these materials are solving two different engineering problems at once.
Exactly. Two distinct problems.
What's the first one?
First is insulation. They offer ultra-low thermal conductivity. The figure our research team noted was 0.0196 watts per meter Kelvin at 25 degrees Celsius.
Okay, put that technical number in context for us. How good is that?
It's about 15 to 20 times better as an insulator than the typical fiberglass bat you would use in a well-insulated wall in your house. It is essentially the world's most effective vacuum bottle lining.
So the energy retention is just phenomenal. But what about the second problem? Don't aerogels and ceramics tend to be really brittle? If you put that on a rocket, won't it just shatter from the vibration or the atmospheric stress?
And that is the second critical advantage. The graphene nanorod reinforcement completely overcomes that traditional problem of ceramic brittleness.
Because graphene is so strong.
Immensely strong. Using it to reinforce the aerogel structure makes the material robust and durable enough for high-speed flight environments and the harsh reality of a launch. So you get both the required insulation and the mechanical strength.
That's amazing. So we're not just insulating, we're stabilizing the insulation itself. And what about internally within the spacecraft's own cooling systems?
There we have the role of nanofluids.
Okay.
Yes. The incorporation of nanofluids, for instance, aluminum oxide and copper oxide nanoparticles suspended uniformly in a cooling fluid, contributes significantly to energy efficiency.
How does that help?
Specifically, our research confirmed that this application can reduce the pumping power requirements in systems like the Orion spacecraft. Now, why does that matter? Because in the context of deep space missions, every single watt of power used to run a pump or a sensor is absolutely precious. This is a non-negotiable efficiency gain that extends mission duration and capability.
Okay, so moving from material science back up to orbit, let's talk about the hardware that really dominates the launch landscape. Starship and the huge strategic pivot that is currently underway.
A very big pivot.
Our research team highlighted the stacking of the Super Heavy booster for Flight 12, which marks the debut of the version 3 Starship hardware.
And the V3 evolution is all about capacity and, crucially, reliability. This version is designed to utilize the latest Raptor 3 engine, and significantly, it increases the payload capacity to over 150 metric tons to low Earth orbit.
Which is just a staggering number.
It is, by a wide margin, the most critical piece of hardware for the immediate future of human spaceflight. It's capable of delivering permanent orbital infrastructure in a single launch.
The hardware is getting bigger, it's getting more powerful, but despite this advancement, the mission timeline for Mars is sliding dramatically.
It is. The original late 2026 uncrewed Mars mission is now delayed until at least 2029. And it was a delay that Elon Musk himself called a distraction.
That one word, distraction, speaks volumes about the current strategic focus, doesn't it?
It really does. The V3 hardware may be getting ready, but the system as a whole is not. The urgent, defining goal for 2026, according to all the sources, is perfecting orbital refueling.
That's it. That is the foundational technology that everything else now hinges upon.
Everything.
But wait, if they can build a rocket that can lift 150 tons to orbit, why is ship-to-ship propellant transfer the hurdle that's causing a multi-year delay to the Mars mission? I mean, isn't refueling just a matter of connecting a couple of hoses?
It is far, far more complex than filling up your car, especially with cryogenic propellants like liquid oxygen and liquid methane, which are constantly boiling off.
Okay.
Without reliable, repeatable ship-to-ship propellant transfer in orbit, which requires precision rendezvous, autonomous docking, connecting hoses, and managing that propellant boil-off while transferring hundreds of tons of liquid Starship, just cannot achieve the velocity it needs to get to Mars.
And just as importantly,
without that, it cannot fulfill its contract as the human landing system for the Artemis III lunar landing mission.
Yep.
The moon right now is the primary engineering driver. Mars is secondary.
And if you look at the industry response to those Starship delays, you see the competition positioning itself immediately.
And
Blue Origin is stepping right into that capacity gap, framing its Blue Moon Mark 1 or MK1 landers as a vital contingency plan for the Artemis program.
And the MK1 is a very different architecture.
Right.
It's designed specifically to mitigate the risk associated with Starship's developmental timeline.
How so?
Unlike Starship, which requires multiple refueling launches just to make the trip to the moon, the MK1 is a single-launch cargo lander. It's optimized for their New Glenn rocket, and it's designed to deliver up to 3 metric tons of payload directly to the lunar surface.
So we're talking about a more measured, maybe a cargo-first strategy. They can land the habitats, the power systems, the communications relays, the rovers, all before humans even arrive.
Which provides a safer, more methodical approach if the super heavy lift system runs into even more delays. It's NASA looking for a reliable and critical plan B.
And they're moving on it.
Absolutely. Blue Origin is already preparing its Pathfinder mission, MK1-SN001, which is manifest for late 2026. This gives NASA a solid, proven alternative path to establishing that critical infrastructure at the lunar South Pole.
Especially since the MK1 uses that high-precision, deep-throttling LOX LH2-BE7 engine.
Which is key for landing accuracy in that difficult terrain.
So while the heavy-lift rockets are grabbing all the headlines, the launch cadence for the massive constellations just continues unabated. It really underscores the shift in how space is being used today.
Relentlessly.
SpaceX conducted the first Starlink deployment of 2026. That was Group 688, carrying 29 satellites and pushing the active total closer to 9,500.
That pace is just astounding. And the impact is now overtly geopolitical. Our research highlighted SpaceX offering free broadband service to Venezuela through early February, right during a period of domestic upheaval.
And that demonstrates just how critical space-based connectivity has become. It intersects directly with global stability and geopolitical maneuvering.
It really does.
Why is offering free broadband during a period of upheaval such a powerful geopolitical tool? What's the mechanism there?
Because, at its core, control over information is power. In situations of domestic instability, local regimes often impose internet blackouts or they severely restrict data flow to suppress dissent or control the public narrative.
But Starlink can bypass all that.
It bypasses all terrestrial infrastructure. It offers a lifeline, ensuring uncensored communication access for people on the ground. This is a classic example of soft power, where a commercial company can exert influence that rivals that of a nation-state simply by controlling access to the information layer of the modern world.
Meanwhile, the established players are navigating their own transitions while still maintaining their commitments.
They are.
ULA's Vulcan Centaur rocket is preparing for its second military mission, USSF-87, and that will carry 2 GSFE satellites.
Those are the Geosynchronous Space Situational Awareness Program satellites, used for tracking objects way out in high Earth orbit. It's a critical national security function.
And ULA is doing all of this under new leadership. Following CEO Tory Bruno's departure, the company appointed COO John Elbon as the interim CEO.
It's a big transition. But despite that, ULA remains fiercely committed to its launch manifest, even as it faces this increasing competition from providers like SpaceX.
Right. SpaceX recently won the majority share of the national security space launch missions that will be flying between 2027 and 2032.
Which shows that the competition for those high-value national security launches is clearly intensifying.
And globally, even the development of reusable technology faces these very grounded constraints, sometimes literally grounded. There's a bit of space-age irony here, isn't there? The ESA's Themis reusable rocket demonstrator, Europe's answer to the reusable booster trend, is facing delays for its initial hop tests.
It is the ultimate irony, and that delay has absolutely nothing to do with turbopumps or engine failure.
It's the weather.
It's purely weather-related, specifically heavy snow and just persistent bad weather conditions at the Swedish launch facility in Kiruna. The project director confirmed they're essentially waiting for spring.
It just highlights that despite all the advanced materials and propulsion technology we've been discussing, terrestrial weather remains a stubborn and sometimes decisive limiting factor to the cadence of the global space race.
You can't beat the snow.
So this strategic shift, this pivot away from the ambitious timeline for Mars and toward the pragmatic, achievable goal of lunar logistics. That's one of the biggest strategic takeaways of the week.
I agree. The moon is no longer just a destination. It's the immediate gatekeeper to the rest of the solar system, and it's demanding that we perfect the supporting infrastructure first.
We love hearing your thoughts on these strategic shifts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the space sector's immediate focus, shifting away from the immediate gratification of Mars and squarely toward perfecting the moon mission logistics.
And that logistics theme is the perfect bridge into our next section, the orbital infrastructure revolution. We're moving from the concept of disposable satellites to actively building a functional, sustainable orbital economy.
Right. And the heartbeat of that nascent economy has to be the gas station model in space. Let's talk about servicing and refueling, particularly focusing on geostationary Earth orbit, or GEO, which is roughly 36,000 kilometers up.
And GEO satellites are immensely high-value assets. They handle global broadcasting, long-distance telecommunications, critical national security functions. They're expensive to launch, and they're long-lived, often designed for a 15-year lifespan.
And when they run out of fuel, they become space junk.
Exactly. Servicing and refueling transforms them from these disposable capital investments that just die when they run out of fuel into reusable long-term assets. This capability allows them to maneuver freely to avoid threats or simply to maintain their station for decades longer than their original design life.
So extending the profitable life of a billion-dollar asset by decades is the core economic driver here. And the technological barriers to actually doing this, the rendezvous, the docking, the fuel transfer, and GEO, those are largely being overcome, correct?
That's what the data suggests. The major hurdles now are much more logistical and policy-related, but the commercial business case is being proven out by concrete missions that are coming up very soon.
Give us the examples. What capabilities are being deployed in 2026?
Okay, so Astroscale US is moving forward with its prototype servicer for refueling, the APSR. This is a commercial hydrazine refueling satellite, and it's scheduled for delivery in mid-2026. It's designed specifically to rendezvous with and service client spacecraft in GEO.
So they're focused purely on the refueling capability.
That's their focus. Then you have Northrop Grumman's Space Logistics, which has its own approach. It seems more centered on life extension rather than just fuel transfer.
How does their system work?
Their system is the Mission Recovery Vehicle, or MRV. It's designed to launch and then autonomously install what they call Mission Extension Pods, or MEPs, onto aging satellites.
So instead of trying to put fuel into the old tank.
Right. Instead of transferring propellant to the satellite's depleted tanks, the MEPs take over the propulsion and the station-keeping functions entirely. It's like bolting on a whole new engine block and a full fuel supply. And these pods can potentially provide anywhere from 100% to 500% more operational life.
That's essentially space surgery. You're extending the profitable life of these aging assets by many, many years. Beyond just propulsion, can these robotic servicers do more complex tasks?
Absolutely. This robotic servicing capability, which was funded in part by DARPA, can also be used for anomaly resolution.
Meaning if something breaks.
Exactly. If a high-value satellite malfunctions, let's say a solar array fails to deploy after launch, an MRV can get up close, provide detailed inspection, and even perform limited repair services. This level of on-orbit maintenance drastically reduces the risk for these high-value assets.
That's necessary maintenance, for sure. But the ultimate goal of orbital infrastructure isn't just servicing the existing systems. It's building entirely new things that are just too large to launch from Earth in one piece.
That's the dream.
And this brings us to in-space assembly and manufacturing.
The ability to construct truly large structures and orbit vast communications antenna, kilometer-scale solar power arrays, or massive, incredibly stable telescopes, that is fundamental to future deep space missions and major science objectives.
And NASA has been championing this through its On-Orbit Servicing Assembly and Manufacturing 1 mission, or OSAM-1.
It was the Pathfinder.
So tell us what OSAM-1 was supposed to achieve. What was the goal?
It was designed to demonstrate all of these transformative capabilities in one mission. It featured the 16-foot Spider robotic arm, which was supposed to assemble a communications antenna in orbit. And it was even going to manufacture a 32-foot lightweight composite beam using an additive manufacturing process right there in the vacuum of space.
So building things from scratch in orbit.
It was the crucial first step toward building the massive infrastructure that we need for the future.
That sounds like precisely the technology we need. Yet, our research team noted a critical nuance here. The OSAM-1 project is currently undergoing an orderly shutdown.
It is.
So if NASA, with its immense resources, can't make OSAM-1 work, what does that tell us about the timeline for true in-space manufacturing viability for private companies?
It tells us that the technical maturity, the cost controls, and the schedule adherence for these incredibly complex systems are still major stumbling blocks. Our research team attributed the cancellation to a combination of factors: continued technical challenges, escalating costs, and major schedule overruns.
But there was another key reason.
Yes, a crucial one. A key reason was a lack of a committed commercial partner for the mission's original secondary goal, which was refueling an unprepared spacecraft. And that reflects a broader evolution in the servicing community toward using prepared, standardized interfaces.
So the mission was just trying to do too much at once. It was trying to manufacture, assemble, and refuel a satellite that wasn't even designed to be serviced in the first place.
Essentially, yes. The specific OSAM-1 architecture proved to be too challenging for the current budget and timeline. Now, while NASA remains a huge champion of in-space servicing, assembly, and manufacturing ISAM, and continues to fund consortiums like COSMIC, the specific execution of OSAM-1 demonstrated the immense logistical and technical difficulty of moving from ground-based prototypes to flight-qualified multifunction systems in space.
And that puts a huge damper on large-scale orbital construction in the near term. It just shows that the technical leap often runs right up against the wall of cost and logistical reality.
It does.
This brings us back to the biggest hurdle you mentioned regarding the commercial viability of the space gas station model, even if the technology itself is proven.
And that hurdle is standardization. The technology for autonomous rendezvous, for docking, for fuel transfer, that is proven, as we've seen with the Northrop Grumman missions. However, the key logistical barrier holding everything back is the lack of standardized docking and refueling interfaces between different satellite designs.
It's the old analogy. If every car had a different shaped gas cap, gas stations wouldn't exist, right? The market just couldn't support the infrastructure.
It is precisely that analogy applied to billion-dollar satellites. If every satellite bus requires a bespoke attachment, a specialized robotic arm function, or a unique fluid line coupling, the commercial viability of scalable servicing just disappears entirely.
The lack of interoperability.
It severely limits the market size, and it increases the complexity, the risk, and the cost of every single service mission.
So how does the industry solve this chicken and egg problem? Manufacturers don't want to design in a refueling port if there are no servicers, and servicers don't want to launch if every satellite is different.
This is where policy has to step in. And the research team noted that the U.S. Space Force is becoming a strategic driver here by requiring that future military and national security satellites incorporate a standardized refueling interface.
A government mandate.
A mandate. It forces the major satellite manufacturers to adopt interoperability standards, which in turn will kickstart the commercial service market by guaranteeing a certain volume of prepared clients right from the start.
We've covered the ambitious science and the expanding infrastructure, but now we have to confront the challenges that threaten to derail this entire enterprise, the earthly friction involving security, health, and regulation.
The hard stuff.
Let's start with a massive cybersecurity crisis that affected one of our biggest space partners.
Our research confirmed a really significant security breach at the European Space Agency, or ESA. The agency acknowledged the theft of approximately 500 gigabytes of highly sensitive data. It was attributed to a group called Scattered Lapsus Hunters, which allegedly exploited a previously known vulnerability.
0.5 terabyte of sensitive data from a major space agency is a huge haul. What exactly was compromised, and why does this matter for current and future space missions?
The stolen data included proprietary contractor documentation from major mission-critical players like SpaceX, Airbus Group, and Thales Alenia Space. But more concerningly, it included operational procedures, contingency plans, and detailed failure modes for mission-critical Earth observation satellite constellations.
Operational procedures and failure modes. So that is the intelligence someone would need to potentially disrupt or even interfere with these systems. This moves beyond simple industrial espionage into potential weaponization.
It absolutely does. It underscores the high-value nature of even unclassified engineering data, and it proves that traditional perimeter security models are failing. The research team noted this incident necessitates the immediate, broad adoption of zero-trust security architectures across the entire aerospace supply chain.
Okay, explain zero trust, simply for the listener. What did the old security model assume, and what does this new model demand?
The old model assumed that once you were inside the company network, once you got past the firewall, you were trusted. It was like a medieval castle.
Yeah.
A hard outer wall, but everything was safe and open once you got inside.
And zero trust.
The zero trust model, in contrast, assumes every device, every user, and every connection is potentially hostile, regardless of whether it's inside or outside the network. Every single access request must be verified and authenticated continuously. It's essential when you're dealing with a complex supply chain involving thousands of contractors and subcontractors.
That sounds like a major and very expensive overhaul for the entire industry, but obviously a necessity given the gravity of this data leak.
It is.
But let's turn our attention to the immediate human element in space. We saw a situation unfold on the International Space Station, the ISS, that highlighted the real, persistent danger of long-duration missions, human health isolation.
A medical situation involving an undisclosed crew member forced NASA to postpone the first two spacewalks of 2026, which were originally scheduled for early and mid-January. It just highlights how vulnerable we are to the fragility of the human body in a confined, isolated environment.
And these weren't routine spacewalks either, were they?
Not at all. They were critical tasks, including preparing the 2A power channel for the installation of the final set of IROSA rollout solar arrays.
Which are essential to bolster the station's power system before its planned retirement.
Right. So a medical issue for one crew member cascades immediately throughout the entire operational manifest for the whole station.
And beyond just the operational impact, this medical incident carries even heavier implications.
It does. NASA is actively evaluating the possibility of an early end to the SpaceX Crew 11 mission, which could require an immediate emergency return to Earth.
Wow.
It highlights the extreme isolation and the critically limited medical resources that are inherent in space travel. While the ISS has some basic diagnostic and treatment resources, any severe condition necessitates a complex and very risky return to Earth. The vulnerability of a single crew member can jeopardize the entire mission schedule and, crucially, the continued viability of the ISS itself.
Finally, we turn to the regulations that govern the speed of the commercial space race. The commercial regulatory crunch involving the FAA's new Part 450 rules. This is a massive, complex challenge impacting every single company that wants to launch or re-enter a vehicle in the U.S.
This is a major pain point for the U.S. commercial space industry right now. They are facing a hard deadline of March 10, 2026. By that date, all existing launch and reentry licenses must comply with the FAA's new Part 450 regulations.
Now, the intent of Part 450 was excellent, wasn't it? It was designed to streamline licensing by shifting from prescriptive regulations to performance-based standards. On paper, it sounds like a great move toward innovation.
The goal was absolutely noble and necessary. The old system was prescriptive. For example, the FAA might have told a rocket company, you must use the specific FAA-approved valve manufactured in this specific way. The new performance-based standard shifts this to, the valve must survive X amount of pressure and operate under Y thermal conditions. It allows engineers to use new materials or consolidate parts via 3D printing to meet the outcome without being forced into an old, expensive process.
And it allows a single license to cover multiple launches.
Which is vital. A single license can cover multiple launches from multiple sites, which is essential given the cadence we see from companies like SpaceX.
But the reality of this transition has been messy, right? Why is a regulation that's supposed to increase efficiency actually creating a bottleneck?
It has been very messy. Industry stakeholders have asserted that the transition process is incredibly complex and resource-intensive. Companies have to spend significant time and money developing all new means of compliance documentation for the FAA to approve.
Yeah, the FAA is struggling to keep up.
That's the other side of it. The bottleneck is severely exacerbated by concerns that the FAA's Office of Commercial Space Transportation, or AST, lacks the increased funding and staffing necessary to keep pace.
The numbers tell the story here. The launch cadence hit 113 licensed launches in fiscal year 2023. You have an absolute explosion of demand hitting a regulatory body that is understaffed and underfunded to approve these complex performance-based licenses quickly.
It's a classic case of good policy intention meeting real-world resource constraints. If the FAA cannot staff up and process those licenses before that critical March 10th deadline, companies will be grounded.
And that's a huge economic threat.
That constraint, if it's not addressed, risks ceding market share and advantage to international competitors who are operating under less stringent or more rapidly evolving regulatory regimes. The consensus from the policy reports our research team gathered is that these regulatory bottlenecks are the primary terrestrial threat to the U.S. maintaining its dominance in the global space economy.
That brings us to the close of our analysis for Tomorrow Unveiled. As we look at the week's events, that central paradox we started with is just impossible to ignore.
Indeed. This week really showed the expanding scientific and engineering potential of humanity's reach. We saw the expanded history of water on Mars, the radical materials breakthroughs like carbon-negative carbon fiber, the evolution of Starship V3, and the emergence of commercially viable orbital servicing models.
But every single one of those advancements is being countered directly by these persistent, grounded constraints.
Major cyber risks, human vulnerability in deep space, and stifling regulatory burdens right here on Earth.
So to recap, we now know Mars was wet much longer than we previously believed, which vastly expands the window for potential life. We learned that our materials are becoming carbon negative and nanotech driven, creating stronger and lighter space hardware.
And critically, that the immediate future of human spaceflight hinges entirely on perfecting orbital logistics. Specifically, refueling, as demonstrated by that strategic pivot away from an immediate Mars mission.
The focus is now pragmatic. Perfect the logistics on the way to the moon first, and then use that foundation to build the deeper infrastructure that we'll need.
That's the plan.
To leave you with a final provocative thought, let's look at the ultimate, most ambitious goal humanity is pursuing: the search for life beyond our own solar system.
The big one.
Our research team noted that NASA recently selected industry proposals to advance technologies for the Habitable Worlds Observatory, or HWO, concept.
And the HWO is intended to be the first mission specifically designed to directly image Earth-like planets around Sun-like stars, and not just see them, but analyze their atmospheres for chemical signs of life, for biosignatures. This is the ultimate science goal, and it demands unprecedented scale and precision.
And the connection here, tying everything we've talked about together, is crucial. To achieve that mind-boggling scale of science, the HWO must leverage the very terrestrial logistics and orbital infrastructure we just discussed.
Exactly. The HWO will be too massive and too complex to launch in a single package. Its optical systems will have to be assembled in orbit, and they need to be stable to within the width of a single atom.
So its success is being designed from day one to rely entirely on in-space servicing and assembly.
Which means the difficulties of OSAM-1 have to be overcome. The commercial infrastructure for GEO servicing must be perfected. Our ability to find life light years away hinges on whether we can successfully navigate the cybersecurity, funding, and regulatory challenges we're facing right now, today.
The success of future deep space science relies entirely on perfecting the terrestrial logistics and infrastructure discussed in this Look Forward on Tomorrow Unveiled.
Keep that thought in mind as you look up.
If you're finding this insightful on YouTube, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
And if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners.
Keep those insights coming, and we'll catch you next time as we continue to unveil tomorrow.